So I'm Saori Nakashita, PhD candidate in Graduate School of Science, Kyoto University. Then I'm gonna talk about flow-dependent large-scale blending for limited area ensemble data assimilation. This work has been done with my supervisor, Professor Takeshi Enomoto. So the topic of this study is the multi-scale data assimilation for high-resolution limited area model, RAM. One of the challenges in RAM is that the RAM-DA sometimes worsens large-scale structures from those in a global model GM due to limitations in the domain size or the observation volumes. This is a crucial problem since the large-scale errors can degrade the convective scale forecast performance of RAM due to the displacement error of large-scale disturbances. So to constrain the large-scale structures in RAM, several large-scale blending methods for RAM-DA, hereafter called LSB methods, have been used in operational forecasts. However, traditional LSB methods often ignore the flow-dependent nature of GM large-scale errors, despite the approved importance of flow-dependent background error in convective scale DA. So this study aims to propose a new flow-dependent LSP scheme based on Ensemble variational framework. And this table describes the traditional LSB methods compared in this study and highlights the originality of our proposed method, nested EN bar. The background LSB scheme used in MetOffice is independent of DA and combines GM and RAM with empirically determined scale-dependent weights. The blending is applied before the DA, and the blended state is used as the first guess for the RAM DA. Since the DA method can be freely chosen, the flow dependency in DA is possible, but the scale-dependent weights usually don't have any time or space dependency. Hillary and Fisher 2008, hereafter called GF8, proposed 3D bar augmented by GM large-scale information. The strength of this nested 3D bar is that the GM large-scale information can be introduced simultaneously with observational information at the analysis step. However, since the background error covariances are determined climatologically, there is no flow dependency in the DA or LSB steps. In contrast, our proposed nested EN bar extends the nested 3D bar of GF8 to an ensemble variational framework, and both background error covariances are estimated from ensemble forecasts. Thus, the large-scale information of GM can be introduced simultaneously with analysis with the dynamically determined weight. So first, I review the alteration of the cost function with augmented GM information proposed in GF8. The cost function, the control variables for cost function x is the state vector in RAM space, and lowercase b indicates the RAM backgrounds, and the uppercase b indicates the GM backgrounds. In addition to the conventional background term and observational term, GF8 introduced the new information about the GM large-scale backgrounds, defined using the interpolation and truncate operator H1. This H1 projects the state vector in GM space onto the low-resolution RAM space. The corresponding control vector is the truncated RAM state, defined using the truncation operator H2. Then the augmented error covariance W is constructed using the three error sources. Here xt refers to the true state for the RAM, and the large-scale error is defined using the previously defined two operators, H1 and H2. Then the error covariance has 3 times 3 components with 5 newly added covariances. First, this error covariance is simplified using the traditional uncorrelated assumption between the background and observation errors. Furthermore, GF8 ignores the cross covariance between the background and large-scale errors based on the statistical evaluations. Finally, the error covariance takes a block diagonal form with background error covariance B, observational error covariance R, and the large-scale error covariance V. As a result, the cost function for nested 3D bar can be formulated as the sum of three terms: background, observation, and large-scale departure. Then we introduce the control variable transformation using the square root of background error covariance B. This is the preconditioning for efficient minimization following Dahlgren and Gustafson 2012. Like the background error covariances, large-scale background error covariance is also determined statistically and usually requires several assumptions on error correlations, such as isotropic spatial correlation or the geostrophic balance, and so on. So now we described our proposed scheme. The augmented EN bar transforms the nested 3D bar cost function using the flow-dependent background error covariances and large-scale error covariances using ensemble estimation. Based on the correspondence between the preconditioned 3D bar and EN bar cost function on the first two terms of cost function, the third term of large-scale departure is also represented using the ensemble weights W and the truncated ensemble perturbation ZB and ZB, respectively. Then the ensemble size K is usually far smaller than the state size even after the truncation. We use the pseudo-inverse of the truncated ensemble perturbation instead of the matrix inverse. So this extension enables us to dynamically determine the relative weight of DM large scales based on the ensemble forecast and relative to the background or the observations. Then the ensemble updates using the information of the Hessian of cost function at the solution of minimization WA following Spassky 2005. So the analysis ensemble is also affected by the large-scale information. Now, nested EN bar is compared against the conventional DA and other LSP schemes using the cycled experiment with nested Lorentz system. Based on Kretschmer et al. 2015, the nested Lorentz system is constructed using the specially one-dimensional chaotic multi-scale model proposed in Lorentz 2005. The nature run is created using type 3 model within a global domain with 960 grid points. GM uses the type 2 model with the 4 times coarser spatial resolution than the nature run. RAM follows the same model dynamics and the spatial resolution as the nature run, but computed in the quota domain. And the lateral boundary conditions for RAM are given by Davis relaxation. Then the experimental design for cycled OC is shown at the bottom part. The 250-day long GM forecast and analysis and forecast are created using the EN bar with 80 members and assimilating 30 global uniform observations. All observations are linear and have error variance 1 and assimilated per 6 hours. In LAM experiments, we conduct 3 types of DA experiments: only LAM-DA, background LSB plus LAM-DA, and nested DA. We use a 3D bar and EN bar for DA methods. The performance of DA experiments are compared against the GM spatial interpolation called NORAM-DA in 240 days after the first 10 days as a spin-up. In nested DA, H1 and H2 truncate GM at wave number 1224 with discrete cosine transformation. And in EN bar, localization is not applied, and the multiplicative inflation factors are tuned manually. Note that our nested EN bar uses larger inflation values than the other EN bar experiments, because the analysis update in nested in bar tends to shrink more than the conventional update without GM information. And we conduct the 5 types of LAMDA experiment with different synthetic observation networks. The first one uses the same uniform observation as GM in the RAM domain, which includes the 7 evenly spaced observations. The other 3 settings put observation density in fixed 30 points at the left, center, and right of the RAM domain. The final settings is similar to the second to fourth one, but the observed locations are moving randomly, which mimics microwave sounders. Then these two figures shows the time averaged analysis RMSE for each experiment. The RMSE values are shown as the difference from norm DA, and positive and negative values indicate improvement or degradation from norm DA, respectively. Left part shows the 3D bar experiments, and right part shows EN bar experiments. In most cases, the conventional DA without LSB, shown in blue bars, significantly degrades the analysis quality than the norm DA, despite especially for the dense and unevenly distributed observations, despite for the increase of observational information contents than the global DA. This large degradation is mainly due to the increase of errors in large scales. On the other hand, the experiments with LSB methods shown in orange or green bars significantly improve this degradation and show stable performances irrespective of observational networks. In 3D bar experiments, the simultaneous assimilation of GM large scales using nested 3D bar outperforms BLSB plus 3D bar, since the RAM 3D bar severely degrades the large-scale analysis. In contrast, BLSP plus EN bar and nested EN bar show comparable good performances. A proposed nested EN bar show best performance on the left, center, and moving observation networks. Hereafter, we focus on the EN bar experiment with moving observation networks. This figure shows the analysis error in state space for EN bar experiments with moving observations. Black curve shows no LAMDA errors, and no LAMDA has relatively large error in the right part of the RAM domain. EN bar in blue curve has large error near the lateral boundaries and is under-dispersive in the entire domain. BLSB plus EN bar in orange curves mitigates large error near lateral boundaries of EN bar and provides more consistent ensemble spread with RMSE. Nested EN bar in green curves improve analysis more than BLSB throughout the domain, which suggests the benefits of dynamical blending using GM flow-dependent forecast uncertainty, despite the underestimation of spread is more severe than the other methods. And to see the DA and LSB impact in spatial scales, this figure shows the analysis error spectra in each experiment. As you can see, the nested EN bar clearly mitigates the large-scale error more than conventional DA and BLSB, and even improve the large-scale analysis compared to no LAMDA. At the middle wavelengths, the LAMDA impacts are shown compared to no LAMDA. So nested EN bar takes advantage of the large-scale error mitigation by LSB and the middle wavelength improvement by LAMDA, leading to the best performance among the other DA methods. So finally, we investigate the impact of LSB methods on the extended forecast from the analysis. This figure shows the deterministic forecast RMSE from the analysis ensemble mean. Grey Sitka curve shows the GM forecast errors, and all the RAM experiments show faster error growth than that of GM. And markers indicate the statistically significant improvement over the downscaling of GM shown in black curves. As you can see, the analysis improvement by nested EN bar is a significant forecast improvement up to 36 hours. In summary, we developed a new flow-dependent LSP method based on Ensemble variational framework. Our experiments show that the simultaneous assimilation of GM large scales with observation by nested DA is more beneficial than background LSB when LAMDA is known to significantly degrade the large-scale structures, such as using the climatological error covariances or assimilating densely observations and so on. And our proposed nested in bar effectively reduce the large-scale errors, especially with dense and unevenly distributed observations in the RAM domain. And the dynamical blending of nested in bar appropriately incorporate large-scale constraint by LSB and LAMDA impact. For realistic applications, we should incorporate multi-scale localization or inflation method with nested DA in bar. So for more detail, please refer to a recently published article in TERAS A. And if you are interested in our scheme, the source code is available from GitHub. That's all. Thank you for listening and happy to discussion.
Thank you very much. A very interesting talk. We have time for some questions, so if anybody would like to put something on the Yopad, if they have any questions, we can still discuss them, please. Okay, so there doesn't appear to be any questions right now, but if anybody comes up with any, please put them into the Yopad for Saori to answer, please. Thank you very much again for your presentation.
Okay, thank you.